So there's a few definitions that I need to use. There's a few proofs from the book that I've decided I'm not going to use class time to prove, even though the mathematician in me would really like to do that. I just don't think it is a good use of our time in the classroom since we have so few minutes in the classroom together. So I'm just going to call upon a few theorems from the book, a few definitions, and then I'm just going to use them in the homework like I've been doing this semester so far. And the first one is the definition of the natural base. Okay, so that's the letter E that we use in mathematics. And it gives a definition here, and we see what that is. And I'm gonna just, I'm not gonna prove that this has to be true. I mean, it is just a definition. I'm gonna make a few comments and try to relate it to something we have seen before in this semester, and then we can talk about. Do you remember compounded interest? So with compound interest, we had things like you had some initial investment, 1 plus a rate over the number of times it was compounded, times the time, which was usually in years. Okay, this was compound interest. So, you know, if you have something like quarterly, that implies that n equals 4. If you have annual, that's just n equals 1. If you have something like daily, that implies that n equals 365. And I might have even teased it a little bit when we talked about it. But what happens when n goes to infinity? What if you are continuously compounding? Okay, that's what nature does, by the way. Nature doesn't do it in discrete chunks, it continuously grows. So what happens when that n approaches infinity? What does that mean? Or what if your bank account compounded continuously? So that's one of the things we're looking at, is that the limit as n approaches infinity of some initial investment, 1 plus the rate over the number of times it's compounded, number of times to t. And what we say is that that is going to go towards this very special number called E. So that goes towards, in this case, that's going to be P, E, R, T. Okay, P, E, R, T, or PERT. If you're one of those counting people, you might have heard of that. But that's the idea. So if something is compounded continuously, it doesn't do it in these chunks. It just does it streamlined, nonstop. How does that work? Well, we say it goes to this very special number called E, which is in your calculator. Okay? You have E to the first in your built into your scientific calculator, and it is a transcendental number. Okay, it's kind of a magical number. And that's the number E. So we're going to use that number E a lot today, and it has special properties, and its derivative is very special. And if you go on to mathematics or you go on into science, you're going to use E a lot, okay, because it is part of the natural world. So we see it happen in our equations many, many times. If you go on to say physics or chemistry, maybe high-level biology. Well, my little friends, someone close the door. Sorry. Okay, so that is just the idea of what is E. Okay, that's just a little precursor. And then very shortly, I'm going to get into problems. That's the majority of what I'm doing today, is just getting into problems. But I wanted to at least give some kind of discussion to what are the things. So you can see okay, if you had some investment and it was compounded continuously, then the number of times it's compounded goes to infinity, and that goes to E. Thought one of those little kids. So I'm gonna have to use my dad voice now. Okay, sorry for the flipping. Now, the next thing I want to talk about is the natural logarithm, or maybe I should talk about logarithms in the first place. So logarithms are the inverse function of the exponential function. Okay, we don't have, I know we just started class, but you'll see how limited amount of time we have to talk about it. The idea with logarithms is, let's say you had 10 squared is 100, right? So the common log, the log of 100 equals 2. What does that answer? So that's the common log. If we see the log without the base symbol, what does that mean? That means what is the exponent that gives you 100? Okay, so this is the inverse. It's like asking the question, that 100 is going in and the 2 is coming out. Okay, that's logarithms. So that's the idea. And logarithms were very, very, very common in math education up until the point of calculators, microprocessors hitting it. So they were way more common in the classroom than they were when we were growing up, and maybe even less so when you were growing up. But anyway, so that's how logarithms work. Now, we just talked about this thing called E, this transcendental number E, okay? And it gets its own special logarithm because it is very, very special. But I'll just mention that this is the common log, and you will see that on your calculator. Okay, so if you just see log, that's common log. That means base 10. Okay, so that's asking what would be the exponent of 10 to give me this number. So that gives us the common log. But what about this natural logarithm? Okay, the natural logarithm is the base E. So if you have log base E of something, we're talking about that transcendental number E, and it gets its own special symbol, ln. ln of x is the natural logarithm. Okay, so you will see that on your calculator as well, somewhere. Natural log. Okay, so you should see on your calculator an log button and an ln button somewhere. Somewhere on our calculators, those are there. And we need those. We're going to need those. Okay, we're going to need those buttons. And yeah, so as of right now, I'm just kind of bringing a few things up. Now, supposedly you've learned all of this before in your studies, but I just thought I might bring it up one more time. Okay, and I'm going to bring up some theorems from the book as we go along, and I'm going to bring up maybe some more definitions from the book. Again, the mathematician in me, of course, wants to spend 45 minutes proving some of this because that's what I'm interested in, but that's not what you're interested in. Of course, what you want to do is you want to do more and more problems as fast as possible. So I'm going to gear it towards that, towards the getting more and more problems done. But I still don't think I'll be able to do nearly enough problems today because there is a lot to be done. But I have some problems picked out, and if I have time, I might make some bonus homework videos later this week, depending on my week, okay? But I'm being pessimistic. I'm already, we're only 13 minutes in, and I'm like, There's never enough time, but it's true. There is not enough time. And this homework, I think, is exceptionally long. So I will say, fair warning, the 3B will take you longer than it normally does. Okay, so if it's taking you however many hours to do this homework, add at least another hour to it. Okay, just be wary. You want to start that one a little early because there's a lot of word problems to look at. But I'm hoping to streamline. Anyway, okay, let's actually do a problem. And the homework does do a good job of being in order to kind of build you up. So I want to do the first 7 problems. So we want to rewrite 27 equals 3 cubed in the logarithm form. I remember doing this in algebra class, so I know at one time you've seen it. We just got to knock the rust off. Okay? So what does that mean? 3 cubed equals 27. And I know this crazy guy was talking something about 10 squared equal to 100. So common log of 100 equal 2. Okay. This guy was talking about that just a second ago. Now we're talking about 3s. Okay. What does that mean? Well, that doesn't have anything to do with E, and that doesn't have anything to do with 10. That has to do with the 3s. Okay. So we need to convert this to log base 3. Log base 3 of 27 equals 3. That is saying that 3 to the third equals 27. That's base 3. Okay, I used base 3. I talked about base 10, which is on your calculator. It's also on your phone calculator as well. I know that on my phone calculator, I can use these. I have to tilt my phone to the side and I can get it. I can get both of those. No, it's on my laptop as well. So you have those buttons. So I thought I would mention this. Now, while I'm thinking about it, you don't have a log base 3 button in your calculator, right? I'm saying you have log base 10 and log base E, which is ln, natural logarithm. But I'm saying you don't have any other ones, presumably. We're going to use this later, but you can use change of base formula. If I have time, I'll prove this. It's a pre-calculus thing. But if you wanted to do log base 3 of x, you can rewrite that as log of some number over log of 3, which you can also do log of x over ln 3. So whatever the number is, you can change it. So you can break that up. And I'll probably bring that up later when I need it for problems. But we don't need it for this one. They just wanted us to build it. Okay. I'm going to try to do the first 7 problems. 7 problems. Okay, what does this one say? Write an equivalent logarithm equation. So we have 10 to the negative 7. And that's 1, 2, 3, 4, 5, 6, 7. Okay, so that's 7 zeros. So what does that mean? Log, and remember, log without any notation, log without any notation means common log. That means base 10. Okay, so I'm just going to write log because I'm talking about this. Log of 10 to the negative 7 equals negative 7. Now, this is not a baffling result. That's just saying that the exponent of 10 to the negative 7 is negative 7. And then we also see what negative exponents equal. You've seen that before at some point in your life. Now we have to remember again, negative exponents means it's a number less than 1. Less than 1 with the negative exponents. Remember. So don't forget common log. Common log. I don't care if you remember that phrase, but it just means that log of x is log base 10. That's what that is. And I want to say it's on my laptop or on my phone. So I have an iPhone. And they have log base 10. So it actually is log 10, right? So some of them will say 10, some of them don't. If they don't say anything, that means base 10. That's the idea. Let's keep going. Convert to exponential, going the other way. Let's see what happens. So we have log base 2 of 4 equals 2. What does the statement mean? This is your base. 2 to the 2 equals 4. I mean, this is a groundbreaking proof. It means 2 times 2 is 4. That's what we've proven here. Okay? So it's nothing deep, but we're just getting just knocking off some rust with some of these logarithms and exponentials. It's nothing super deep yet. This one I wanted to do just because I thought maybe the fraction might give us trouble. So we want to rewrite this as an exponential. This is log base 27 evaluated at 9 equals 2/3. Okay, this is my base. Okay, so 27 to the 2/3 equals 9. And if we bring that, that's the answer. So that's the answer. That's all you have to do. If you bring that back to our radicals, you could say, which I probably shouldn't be saying. In fact, I'm going to take it back because I don't want to bring that up right now. It'll only make things worse. Okay. So we're just logarithm to exponential, exponential to logarithm, which is something, it's just an algebra concept, but we're just, or if you haven't seen it in a long time, you don't remember seeing it ever, now's the time we have to learn it. Okay, so we have to learn that. Okay, but this one. I have an equation here. We have log base 4 of y equals 3. Solve of y. Well, can we? So I think what we need to do is convert it to an exponential and see what happens. Let's see what happens. So this is base 4. This is my base. So that's 4 cubed equals y. Well, I can evaluate that. 4 times 4 is 16, times 4 is 64. So that means y equals 64. Okay. So by converting it, I was able to solve it. Okay, I didn't multiply, divide, add, or subtract. I converted it to an exponential to solve. Okay, so convert to solve. Which that might be a little strange, especially when the problems will get more complicated. But that is a technique that we can use with logarithms, exponentials. We can convert them back and forth since they're equivalent statements. And sometimes we can work on the problem using one technique rather than the other. Very similar to, remember, our square roots. So sometimes with our square roots, we convert those to our exponents, and then we were able to do different things using the exponents. So it's a little bit like that. Sometimes you can rearrange the problem so you can work on it in a different way. All right, this one is having us solve for the base. We haven't seen one of these yet. This is log of base b. We don't know what it is. It's evaluated at 2, and it equals -1/3. Okay. How do you do that? Well, let's remember how to do this. So that's my base. So that means base b to the negative 1/3 equals 2. Okay. Let's go to something we do know. Log of 100 equals 2 because figure that out. That's common log. So 10 squared equals 100. This is base to negative 1/3 equals 2. How can we solve for b? Solve b. Well, my thought is we're going to have to play with the exponents. That's all I can really think we could do with it. So I need to do something with the exponents. If it was squared, I just want to, what if, this is what my brain would do. What if it was b cubed equals 8? Okay, if it was b cubed equals 8, I would just take the cube root of both sides. That's what I would do. And I would get 2. Does not solve my problem, but I mean, that's just where my brain's remembering how I solved problems like that before. How would I solve something like this? I'm thinking we need to put both of them to an exponent of some kind to solve for b. So I'm thinking if I pick the right exponent, I could do it to both sides, and it would reduce that exponent to 1. So I'm thinking, okay, I have negative 1/3. What exponent could I put it to that would cause it to be positive 1? To me, I'm thinking if I go negative 1/3 times negative 3, that turns it into 1, and that's solving for b. They have to do it to both sides. So now I think b equals 2 to the negative third. All right, well, if you remember your exponents, that's just 1/2 cubed. That's just 1/8. But that's something going back for me, going back all the way to an intro algebra, intermediate algebra chapter that I went over. Okay. Are there any questions about that technique? Is that okay? Does anyone want to see me do it again? I mean, all of this is review, but it's important. All of this is important review. Sure, I got a picture. So the idea is that you're solving for the unknown number if the exponent has 1. So I just thought, okay, what number would make it 1? That's the idea for me. Any questions about that? That's the first chunk I wanted to touch. Okay, next part, I'm going to skip down to problem 10, start talking about these. Here we have e to the x equals 5. Solve for x. Well, e to the x equals 5. The x, solve for x, the x is in the exponent. Right? So it's not like 2x plus 5 equals 8, where I can just simply add, subtract, multiply, or divide to solve for x. The variable is in the exponent. So these techniques are not going to work for me. Not for this. I have to come up with something else. What else can I do? How can I solve for an exponent? Well, you rewrite this as a logarithm? Is that possible? Can you rearrange this so it is a logarithm? Let's try it. Is there a way to rearrange this? Again, when I'm dealing with logarithms, I think back to something I know, and then I can go to something I don't know. I know 10 squared equals 100, and log of 100 equals 2. That's something I know, and I can take that to the bank. Now I'm going to natural logarithms. Those are kind of weird. All right, I mentioned that logarithm base e gets its own special symbol, ln. ln is the natural logarithm base e, so I'm going to use that. So the logarithm base e of 5 equals x. So by rearranging this, I have solved for x. So x equals the natural logarithm of 5. I did it. But then MATLAB comes and tells me, type an integer or a decimal rounded to 4 decimal places as needed. So it's not going to be happy with me if I type in ln of 5. I would be happy if you wrote that down for me, but it's not going to be so happy. So I'm going to call upon my calculator, and I'm going to evaluate this. So I have the ln button on my TI-83. We all have it somewhere. ln of 5 equals 1.609, and then you just round appropriately. I had to use a calculator to find the decimal approximation. Okay. Any questions about that one? So that's kind of strange. Now we're taking logarithms of transcendental numbers here. That's kind of weird. Any questions about that? Well, I have the chat pulled up, so just stop me if you have a question or I do something wrong. The next one I wanted to go over, 10, 11, 12 is the next one. Okay, let's try this one. E to the 2t equals 2400. Solve for t. What can I say? Well, we know we're going to deal with ln, that's for sure. We know that 10 squared equals 100. Log 100 equals 2. We haven't really dealt with something like that, have we? Or it has that 2? Or the thing itself has an coefficient. If it dealt with something like that. Seems like we would write 2400 somewhere. Ideally, we would have t here. If everything worked, but I don't know what to do with that 2. So we haven't played with that before. So, So where does the 2 go? Does it go here? What should we do? So this is where it's difficult because we're just looking at examples rather than problems. But I believe the 2 should go here. Let's see if that works. So I'm going to try that in my calculator. Let's see if we get it. So 2 times ln, because we're doing natural logarithm, 2400. Okay. It was supposed to be. 0.5 times natural log of 24. Why is it 1/2? E to the 2t equals 2400. We take the natural logarithm sides. Going to get by exponent rules. Four hundred divided by 2. So this is something that I go over in pre-calculus. Don't know when the last time you took pre-calculus. But if you take the natural logarithm, actually, if you take the log of anything, let's do log of a to b t, you're going to get b t. Okay. It's going to bring down that exponent by taking the natural log. This is not a derivative. This is taking the natural log of both sides. It would also be true if you took the logarithm of both sides. But we want this to go to 1. So taking this, natural logarithm of e goes to 1. Because they're inverses of each other. Just like the natural logarithm, the logarithm of 10 equals 1. So ln of e equals 1. That's the idea. Let me say it one more time. Hopefully more clearly. E to the 2t equals 24. We want to see what does t equal. Solve for t. I claim if we take the natural logarithm, both sides, what's going to happen? 2t comes out, exponent comes out, natural logarithm of e, ln 400. This goes to 1. 2t equals natural logarithm 2400. So t equals 1/2 ln 2400. Okay. So again, this is a pre-calc thing, but sometimes in our class, the pre-calc is harder than the calc. Either way, the exponent's coming down. Any questions about that? All right, I got another one that's similar to this. I need to go over. We'll go over 12. Now we want to solve for k. Solve for k. So what do we have? We have 20 e to 6k equals 60. This is similar to something we just had. Let me do a different color. So this is like e to the 6k equals 60. We just did that problem, figured out how that worked. How did we do this? We took the natural logarithm of both sides. And that gave me 6k natural logarithm e equals natural logarithm 60. That goes to 1. K equals 1/6 ln 60. That's what we did in the previous problem. Okay. What are we doing in this problem? The thing that is added in this problem is we have a coefficient there, and we need to isolate it. So it turns into something like the previous problem. So I'm going to divide by 20. So I get something that's like the previous problem. If I do that, Then I have e to the 6k equals 3. Now let's take the natural logarithm of both sides. Six k ln e ln 3. Natural logarithm of e just goes to 1, just like common log of 10 goes to 1. So we have 6k equals ln 3, and plus k equals natural logarithm of 3 over 6. This one was okay with the exact solution, so I didn't have to type it. Questions on this one? So what did we learn? We learned in this problem that if you have a coefficient with the e, we need to isolate the e before we take the natural logarithm, both sides, okay? So you can divide both sides, almost like you would going back to elementary algebra. 2x plus 6 equals 10. In this, you want to isolate the 2x first by dividing by 2. So you would subtract 6 on both sides, then divide by 2. Okay. Here, we're dividing by 20, just like we would divide by 2. Isolate. The new stuff is taken in that. Well, technically, this is review, but you want to take the natural logarithm of both sides to solve for it. So we haven't even started the calculus part yet, but I know that many of us probably need the review. And if I recall, when I was in your spot, I needed the review too. So luckily the homework does that for us. Any questions about this chunk, these 3 problems? Can I get a message from the chat? Is this review? Do you recall doing this before? Do you guys remember problems like this before? Have you seen this? Yes or no? Have you seen this before? Okay, good, good, good. I mean, I know, sure we all need to practice with something like this, but maybe you've at least seen E logarithms before. Let's go to 15. We want to solve for X. Solve for X, okay? Easier said than done. We have 5 ln x equals negative 15. So what do? We do. Okay, well, before we had e to the x equals a number. Now we're dealing with ln x, right? Before we were dealing with something like that. That was the type of problem we just did. Just did something like this. Now we have natural log. So now we're dealing with natural log. How did we deal with e to the x? Well, it turns out we took the natural log of both sides. So I wonder if there's something like that we would do to this. Anyway, I think we should isolate it as best as we possibly can. I'll divide both sides by 5. If I do that, I get the natural logarithm x equals negative 3. Somehow I have to solve for x, and x is in the argument of this function. X is in the argument of this function. Okay. Again, how did we solve this? The way we solved this was we took the natural logarithm So there we had to take natural logarithm. There's something like that going the other way. Now we want to go the other way. So before we took the natural logarithm of both sides, I'm going to call it exponentiation. We're going to take everything to be the exponent. Okay, let's see what happens. If I do this, e to the ln of x, e to the -3. Okay, everything became the exponent. Just like before, I took the logarithm of both sides, natural logarithm. Here, I'm putting everything as the exponent. If I do this, then because those are inverses of each other, this just becomes x. So e to the ln of x is just x. They're inverses of each other. So that's x equals e to the -3. Well, I think that's the answer, but it says enter as a decimal, so I'll need some help with that. Hopefully my friend calculator can help me. I think if I hit second and then the ln button, e, and I had to do a little rounding, but that's the nature of the beast. So technically all of this is pre-calculus. We haven't even done the calculus. But in our class, usually the pre-calculus is harder than the calculus. So it's worth our time doing this. A lot of times in this class, we have to do a lot of work to get to the point where we actually do the calculus. Calculus is that bad. All right. Hold on to those ideas, okay? We're gonna really need them. Everything is just review, but I think you could also, if you've never seen this before, I think you can learn it right now. But these techniques, taking the natural logarithm of both sides and putting everything as the exponent, really, really, really helpful, okay? And that's going to be really helpful because we're going to end up needing to manipulate certain things to start taking derivatives of certain things. So that'll be helpful to us. All right, so that was 15. The next chunk I want to go through is starting at 20. We're going to take the derivative. We're going to take the derivative. Now, you might say, well, that sounds terrible because so far we've had to do quite a lot of algebra just to do this. What on earth are you going to tell us to do to take the derivative? It turns out that the derivative of e is one of the simplest derivatives that exist. So that's kind of weird. E is a very, very magical number. And one of its properties is that e to the x, or one of the properties of that function, is that it is its own derivative. Can you believe that? d over dx of e to the x is e to the x. So one of the properties of this is that it is its own derivative. That's pretty special. In fact, it is the only function that is true. First derivative, that's not true for second derivatives, but first derivative, it is true that it is its own derivative, and that is one of the ways that you can actually define it. But we defined it using limits, and that's good for us, okay? All right, so if that's true, then I guess I could just use chain rule for this thing, okay? So this is one of the theorems in the textbook, and I told myself I would write that down somewhere, and I've already lost it. Oh, maybe I have it. Just in case you're interested. It is theorem 5. Chapter 2. If you want to see a proof of that, which is the thing that I want to spend all our class time on is proofs, but I can't. So I'm just gonna say, there's a theorem up there, and then there's some pretty good videos in modules if you're interested in a formal proof of that with limits and that kind of thing. But I'm just gonna go straight to application. So here we have f of x equals E16. It can be any number, any real number. You can think of this as e to the u, right? Where u equals 16x. du dx equals 16. And I'm claiming that du is just itself. It doesn't change. Okay, so df dx equals df du du dx, all to say that you just bring down the number. That's really it. You're bringing down the 16. That's it. That's all you're doing. Okay, because it's its own derivative, well, you take the derivative of the exponent, but since it's just that, the x goes away, so it's just multiplying by that constant. So it's unbelievably easy. Okay, actually evaluating it is really easy. So that's pretty cool. Finally, we hit something that's easy, but of course, I want to go over why, but I'm trying to focus on how. Okay, let's see what happens here. We want to take the derivative of this. So this is broken up by subtraction. And at one point I proved, or at least I don't think I proved anything, but I showed that if something's split up with addition or subtraction, that you could take the derivative separately. So you don't have to do it all at once. It's only when multiplication and division you have to do it all at once. So if I take the derivative of this, I can take it by pieces. Okay. So f prime of x, first it's just derivative of x to the fifth. That would be 5x to the fourth. That's no trouble. And then we have minus 4e to the 9x. If you believe me before, this is e to the x, then you can just bring down that 9. And so you would get 4. I'm going to kind of show where I'm getting this from. I'm bringing down the 9, so I get 4 times 9, which is 36, right? So this is 5x to the 4th minus 36e to the 9x. Okay, that's where the 36 is coming from. The 9 is just coming down. Okay, so that's pretty special that we have this function that it is its own derivative. And when that happens and you just have that one number as a coefficient, that number just comes down. Okay, just comes down. So if you had like second derivative, it's going to come down twice. Third derivative will come down 3 times. Okay. That's the idea. So pretty easy in actually performing it. Well, I say that, but then here we go. At x to the 8th, e to the 4x, that looks like two functions being multiplied together. Or I could break it up as that. If you allow me, I'm going to call this y equals x to the 8th times e to the 4x. What if that was f? What if that was g? Do you remember our product rule? That f times g is f prime times g plus f times g prime. Each of these are easy. We just have to build it up. So first, what's the derivative of x to the 8th? It's 8x to the 7th, e to the 4x. Okay. Add. First derivative, leave it alone. Second derivative, looks like we're going to bring down the 4. E to the 4x. Still not bad. 8x to the 7th, e to the 4x plus 4x to the 8th, e to the 4x. Okay, that's the idea. Okay, so product rule, but we're just adding e to the x in that mix here. And we need to at least believe me today, derivative of e to the x is e to the x, even though I haven't proven it. That's the idea. So that's playing with product rule. Let's see what the next question brings. Quotient rule. Sorry. Here we go. F of x equals e to the 5x over x squared. So we want to find the derivative. That looks a lot like quotient rule. What was quotient rule? F prime times g minus f times g prime over g squared. Each of these are fairly easy. We just have to build it. Right? So if I let f of x equal e to the 5x and g of x equal to x 20th, we want to find quotient of this. Quotient rule. So the derivative of e to the 5x just brings down that 5. So we get 5e to the 5x times x to the 20th. Okay. Minus from the formula, derivative of x to the 20th is 20 x to the 19th times e to the 5x. And then on the bottom, we want to square that. So that's x to the 20th squared. And 2 times 20 is just 40. I think that's fine. So I had to use quotient rule for that, but that's okay. Hopefully, we have practice with that. Okay. That makes some kind of sense. What about this one? We have e to the x to the third plus 7x. So if I'm reading that right, that's e to the x cubed plus 7x. That's how I'm reading it, what the computer is saying. And we want to find the derivative of this. Okay, well, I think it might be a good time to think about chain rule. So if I let u equal x cubed plus 7x, du dx equals 3x squared plus 7. And I know that dx of e to the x equals e to the x. So by chain rule, df of dx equals df du times du dx. Well, e to the u, derivative of that is just e to the u. So that's just what we had originally. Times the derivative of u, which is 3x squared 7. And the way I have it written here, I wrote it I think the computer would agree either order, but I know that it agrees with this, so I'm going to rewrite it. So I use chain rule there. What does that mean? Well, it just means that it's bringing down the derivative of the exponent. Okay? When it was just 9x, it just brought down the 9. When it's x cubed plus 7x, it's bringing down the derivative of the exponent. 25, what does that bring me? All right, we have a square root to play with. You can probably guess what my first move here is. I prefer exponents rather than square roots because I know how to deal with them. So I'm going to rewrite this as e to the x plus 19 to the 1/2. Okay. And it looks like I'm going to have to use chain rule again. So I'm going to let u equal e to the x plus 19. And if that's the case, du dx equals just e to the x. The 19 would just go to 0. dy du is 1/2 u to the negative 1/2. That's going back to what we did last week. And I can rewrite that with the u we have. 1/2 e to the x plus 19. So I just need to put my pieces together. So dy dx equals dy du times du dx. dy du is 1/2 root e to the x plus 19 times e to the x. E to the x to e to the x. That's the idea. Questions on that one? Questions, comments, concerns, criticisms? I got one more from this chunk I want to go over. 26. Second derivative. All right. Well, if I can take one derivative, I can take another, I hope. It says find d squared w over dz squared. So find the second derivative with respect to z. Okay. So we have w equals 2z squared times e to the z. That looks like product rule to me. So w equals 2z squared. Let that be an f. E to the z, I'll let that be a g. Okay, just think of these as two different functions. And I know my product rule says f prime times g, f times g prime. So I just need to figure out those pieces. My f prime, in this case, that's squared, so that would just be 4c. And my g prime is just e to the z, so that's e to z, because it's its own derivative. This is only for the first root. All right, so w prime, single prime, is 4c e to the z plus 2z squared e to the z. That's first derivative. It wants second derivative. So that means I have to take the derivative of this thing. Okay. I do that. Looks like I have to do product rule again. That would be an F. That would be a G. Do product rule again. This is like F tilde. And that's still G. So I have to do it again. That's the trouble with second derivatives. You just got to do it all over again. All right, but what's this derivative of 4z? That's just 4. So that's not too much trouble. So that's 4e to the z plus 4z e to the z plus 4 z e to the z plus 2z squared e to the z. So that's the derivative. Second derivative. And I see that I have two of the same thing, so I can put this together. Questions on that? Let's take the derivative, do the best you can. You gotta take it again. Take it again. I'm going to test. Does anyone want me to do it again? You get it. We'll do it again. What about online folks? Does it make sense? They're quiet. Oh. Vega, does that mean you want to see it again, or yes or okay? Cassandra. Okay. I asked too many open questions. 26. And let's go down to 29. Find an equation of a line tangent to the graph g of x equals 4e to the negative 6x at the point 0, 4. Okay, find the tangent line. Classic Calc 1 question. Find the tangent line. All right, so we're given g of x. Okay, what was our technique for finding the tangent line? First thing you have to do is find the derivative. In this case, we want g prime of x. Okay, so that's first step. Second step, g prime of whatever point they give us. In this case, that's 0, but that changes from the problem. They want the tangent line at this point, so I'm going to evaluate it at 0. This gives me my slope. That gives me the slope of the line. Third, y equals mx plus b. Find b. I'm going to find that y-intercept. That's the steps I want to take. So let's do it. All right, g prime of x. Well, e to the x is its own derivative. So the derivative of negative 6x is just negative 6. So we're going to get negative 6 times 4, e to the negative 6x. Okay. 6 times 4 is 24. Go. So that's what I think the derivative is. Now they want at the point 0, 4. So I need to evaluate this at x equals 0. If I do that, the e part just goes to 1 because anything to the 0 is just 1. So I think the slope of the tangent line is that number, negative 24 in my version. Okay. Now, y equals mx plus b, I'm trying to find a line. I think I know what the slope is. They gave me a point, so I can plug all that information in and solve for my y-intercept. 4 equals negative 24, 0 plus b. That goes to 0, 0, b equals 4. Implies that the tangent line is, throw in therefore the tangent line is y equals negative 24x plus 4. Step-by-step guide to find tangent line. Okay, and don't forget what the tangent line is. Tangent line is the line that has the same derivative as the original function, but it's a straight line. Okay, it's a straight line. So we might have something that's curvy. Okay, but if we want the tangent line, say there, be that one. It has the same slope. Okay, that's the idea. Classic Calc 1 question, find the tangent line at this point. I can't remember, it's on your midterm, but it probably is. I mean, that's just one of those classic ones, and I don't remember which one it asked for. I'll have more to say about the midterm next, but at least for now, that's how you find the tangent line if it involves E. That's 29. Next one I want to talk about is 32. And in this, we need to talk about what is the derivative of the natural logarithm. There's a nice proof in the book. Maybe you can see that. Yeah. So there's pretty good proof in the book that shows that by chain rule, you can solve for the derivative of the natural logarithm. And in this case, I mean, it's a little sneaky, but they're putting everything to the exponential, then they're taking the derivative. The derivative of a constant is just 1. Okay, so then it's just x times whatever the derivative is equals 1. And so the derivative of the natural logarithm equals 1 over x. And that's just going to be something that you're going to have to memorize, just like every calc student before you. We just need to remember that it's 1 over x. Now, it'll get really confusing when we talk about antiderivatives. You'll have to remember, okay, which way does it go? But this is really, really important thing to remember. So this one's got to go in your notebook. Okay. And you probably want a cheat sheet when you're taking the test, because you want to remember that. Let's see, do you think that's a helicopter or building?
That's what it sounds like.
What is that? Okay, the building is shaking a little bit. I think it's a helicopter. It's gone away now. Okay, so that's coming from the textbook. Let's see if we can find it. So you could think of this as two functions, which is overkill, but you could. The derivative of f just equals 0. Derivative of g we claim is 1 over x. Okay? So I think the derivative of this f of x just equals 12 times 1 over x, or 12 over x. That's only because of this proof here, or theorem. I think the book calls it a theorem. It is. It is theorem 7 in the textbook. But you'd probably want it on your cheat sheet, just to remember. The derivative of the natural log is 1 over x, but there's a pretty good explanation of that. It just has to do with chain rule and that sneaky thing we did with putting everything as the exponent. That's 32. It'll give me a little bit more of your time. I'm going to go over a few more problems dealing with this. Okay, so we have natural logarithm of 13x as opposed to just x. D over dx, ln x is 1 over x. If that's true, then what's the derivative of something that has a coefficient argument? Well, you could say f of u equals ln of 13u. Well, I take that back. Let's let u equal 13x. So du dx just equals 13. Yeah, that's not what I want. I don't think that's what I want to do. What? Why does 13 go away? So the 13 is going to go away because when you take the derivative of the argument, it's going to go to 1. So with this, so this is chain rule. What is df du? 1 over u. What is u? 13x. So that means this equals 1 over 13x times 13. Let's see, I write times. Sandra missed what your question is. It says, will problems like this always be 1 over x? Problem 33. So I claim that if it has a coefficient like this, that the coefficient will go to 1 because of whatever it was, whatever this was, that reduction is going to happen. So let's say, do you have your homework pulled up?
Mhm.
What coefficient do you have?
I had 7.
7 is good with me. F of x equals ln of 7x. Okay, I claim will still be 1 over x because you'd have 7 over 7x and it'll just reduce. It'll just reduce. Just like my 13 just like your number, whatever. Maybe this is problem 33, maybe you have 33. It'll just reduce because of that. Okay, so that's kind of nice. That's kind of nice. All right, that was 33. Still have more problems I want to go over. All right, you guessed it. So we have, I think we're gonna have to call this product. What if y equals x to the 7th ln 6x? Well, we just played with ln with an argument inside, so we kind of know how that works. What if this is f? What if this is g? That's f prime, g, f, g prime. So y prime equals 7x to the 6th ln 6x plus x to the 7th. And then I think we proved and almost proved that the derivative of ln of some constant times x just be 1 over x itself. So that'd be x to the 6th. And even if you forgot that, it's just going to be one more step where you can show that that's true. So that is 34. And I was hoping to get all the way to 38. Five, quotient rule. Y equals ln x over x to the 5th. What if we said f of x equals ln x and g of x equals x to the 5th? Quotient rule says f prime times g minus f times g prime all over g squared. Okay. So y prime is the derivative of ln x, 1 over x, to the 5th minus ln x, derivative of x to the 5th, which is 5x to the 4th, all over x to the 5th squared, which is just 5 times 2, which is 10. That becomes x to the 4th minus, just write it like that. Quotient. It's 35. What about 36? This is ln of a function. So I think we should probably use chain rule for this. That would be wise. Okay. Du dx is 10x minus 9. Okay. If y equals ln of u, then dy du equals 1 over u, and I let that equal 1 over 5x squared minus 9x 7. Okay. So that means that dy dx equals dy du du dx, and that is 1 over 5x squared means 9x plus 7 times x minus 9. X minus 9. 5x squared minus 9x plus 7. Look at more problems I want to do. D of x equals natural logarithm x to the third. Okay. Y equals ln x to the third. Let's let u equal ln x. If I do that, du dx equals 1 over x by our theorem. Means that y equals u to the third. So dy du equals 3u squared. 3 ln x squared. So dy dx equals dy du times du dx. dy du is 3 ln x squared. Du dx was 1 over x. Yeah. That the idea. So still, really, this is more of an application of what we learned last time with our chain rule, product rule, quotient rule. That was kind of the harder stuff. Now we're using that to study logarithms. For 37, can I do one more problem before break? 38. Find the equation of tangent line. Classic. All right, we have f of x equals ln of x to the fifth, and they want it at x equals 6. Okay. Step-by-step guide. First, find f prime of x. Second, evaluate f prime at whatever they tell you. In my case, it's 6. Third, that's your m. So y equals mx plus b, and you want to find the y-intercept. And you got it. All right, so let's do it. So what is f prime of x? Well, that's going to be 5 ln x to the fourth times 1 over x by chain rule. That's 5 over x ln x to the fourth. Okay. They want it at x equals 6 in my problem. F prime 6 is 5 6 ln of 6 to the fourth. I'll need some help with that from my calculator. And it also says type your answer in slope intercept form. Do not round until the final answer, then round to 2 decimal points. Okay. So I need 5 6 in my problem. Natural log at 6 to the fourth. Okay. Eight, 9, is my slope. So there we have it. And then have my slope, got it. They want an x equals 6, so I need my y. The previous problem, they gave me the point. In this one, they don't. So I need to evaluate this at f of 6, ln 6 to the 5th. So I need that point as well, because they didn't give it to me. It is ln 6 to the 5th. It's like 18 something. 18.47. They told me not to round in intermediate steps. You know how it is. Last problem, they gave us the point. 6 something. Here, they didn't. They left me to find it. So I did. Now, I can say y equals mx plus b. 18.47 equals 8.59 times 6 plus b. Solve for b. Minus 5. B approximately equals negative 33.07. So therefore, my tangent line approximately equals 8.59 times x minus 33.07. Okay. Questions, comments, or concerns about that one? One more problem, if we had time to talk about. Let's talk about that. I don't think I'll take this too much time. Then we'll take a break. I want to find the derivative, first derivative of this. Okay, what happens? Well, if you let u equal 8x, du dx equals 8. So f prime of x just equals 2 times 8 e to the 8x, 16e to the 8x. Okay. That's a little cherry on top for week 3 on A. Easy stuff. That was probably one. Okay, so those are the problems that I thought we might have time to talk about. There are many other problems in the homework, and some of them are word problems. I have all of those notes are going to be posted at midnight tonight. If you're interested in my notes, I know you won't be staying up all night waiting for my lecture notes to release. But whenever you get to the homework, you can refer to my notes as well. And I might, if I have time, I will try to make some bonus videos of extra tricky problems that are word problems if I have some time in the next few days. But I think that's what we have time for part A in the lecture today. Okay, so I am going to take a 10-minute break. Then I'll come back and talk about part B. And solar problem. So I'll be back in 10 minutes. Okay, so there is a lot to be done, and definitely set aside more time for part B than you do for, I mean, in my opinion, set aside more time for part B than you do normally for your homework. Maybe set aside an extra hour at least, because there are a lot of word problems in this one, and so there's a lot of steps that you need to go over. And that would be something that I have notes over. You're going to see notes. I'm going to go over some of the problems that help with building up the theory. And then if I can, I'll give you a couple extra videos of particular problems, especially that there's a silly stamp problem. That's kind of annoying. It doesn't mean it's hard. It's just kind of annoying. But all of the problems, I believe, have a step-by-step guide. So there shouldn't be any problems. You'd be completely on your own to do. But anyway, let's just get into it. So the first problem, it says find the general form of f if f prime equals -5 f of x. So this is kind of strange. This is saying that df dx equals -5 f of x. So really, that means, well, they're giving us the derivative, but I didn't see this when I first took calculus. This is actually what differential equations is. So that's past calculus. Once you complete calculus, if you go on into math, after calculus, one of the classes is differential equations. So that's one of the offshoots of calculus, and that studies derivatives, and you're finding the original function. And that's what we're doing here. So this might be your first differential equation. That's pretty cool. So it's saying the derivative equals -5, the original function. Well, what function do we know that is its own derivative? Well, that's e to the x that we've been talking about, right? So we've been talking about this e to the x, dx, e to the x is e to the x. That is to say dx, e -5x is -5 e -5x. Okay? That's what it is. Now, we don't know what the original constant was, but that's the idea. Okay. So in this, we don't know what the original constant was, but it's what is the function that is of the original. Okay, so we have this constant that we don't know what it was because we can't see the original function, but we know what would give back itself. Okay, so it's e to the -5x because e to the x. And then there's some unknown initial condition that we are not told about. If they gave us a point, we could solve for it, but they didn't. So we're just going to say it's a constant. So capital C for constant. Sometimes we use K for a constant, but we're going to use K for something else today. Right? So that's actually your first differential equation. So you're doing great. All right, find the general form of a function that satisfies dA of dt equals -9 of a. Very similar. So dA dt equals -a. And a is a function of t. So what function do we know that gives back itself and a constant? Well, that's e to the x. So I think a of t has to be e to the -9 t. I don't know what the initial condition is. Could have been 1. It could have been some other number, but we'll just say it's some number, whatever number we started with. We're going backwards now. So we're going backwards. So we're starting with the derivative and finding the original function. That's pretty strange, but we can do that because it's of its special property of it shooting back itself. So that's the first two questions that I wanted to go over. question 1, question 2. Now I'm going to skip all the way down to 13. I'm going to skip quite a few word problems. The only thing I want to just mention to you, this is one, I left it incorrect because I wanted to show you. Watch how it's given to you. Definitely watch the instructions. So that was something I got wrong just because I didn't round to the nearest million. I would write how many millions I have. So watch those instructions, okay? Watch those instructions. I might give another video later this week about how to do this. I think the explanation of the other ones should be fine. And this silly stamp problem. This might be another one you'll see again. The silly stamp problem is very convoluted in my opinion, and there's not too much exciting about it, but you come up with the equation of the stamps, and the confusing part is at the end when you find out how much they save. There's not much exciting mathematics that goes into it. It's just a lot of convoluted steps that you have to take. So you might see some videos about 5 and 8 tomorrow or Friday. Okay. So that will be exciting for you, I know. And those are only if you want them. You don't have to watch them. Those have step-by-step guides. So if you don't want to look at them, you don't have to. I don't want to make it sound like you're forced to see those, okay? It's just for your help if you want it. Right? Anyway, so half-life. You maybe have talked about half-life before in your studies. I don't know. Have you seen Half-Life before? Have you seen Half-Life before? So the idea is that things decay. You probably have talked about, if you talked about exponential growth or decay, you probably talked about half-life once or twice. But certain elements have half-life. So there's a certain time where you have half of what you originally had. And since these elements or isotopes or what have you, since they're natural, they are naturally decaying, which means they're continuously decaying. So we're going to use E. But you could have a bank account that decays over time, but it would decay over, at most seconds. That would be the fastest you could really do it. Anyway, so half-life. It's saying that for a particular radioactive element is 12 minutes. So they're giving us the T here. T equals 12 minutes. The decay rate is what we're looking for. What is the rate? That's what we're looking for. It says half-life. So with this question, we have to bring quite a bit with us. So it is naturally decaying, which means it's continuously decaying. Okay. R is going to end up being negative. This is decaying, but we'll see that in just a second. We're going to try to figure out what that R is. Okay. So again, well, maybe you've played the video game Half-Life. That actually, there's a title of that. But other than that, radioactive substances, they decay, and then that's how they're able to determine how old something is because of how much the isotope is. So it's kind of interesting that you can date things by this process. But this is talking about half-life. So what we're going to do, since we're talking about half-life, we're going to say y over y naught, that's the starting point, is 1/2. Whatever it started with, whatever it ends up to be when we're interested in it, that's half, because we're interested in what's the half-life. So we're saying y over y naught is a half. So that means we're going to have 1/2 equals e to the RT. This is when you're talking about half-life. You're going to want to use this for any question that talks about half-life, or if you're studying it. We can solve for the R because we know how long it takes for it to have a half-life, 12 minutes, okay? So that means we can say 1/2 equals e to the R 12, and this will give us in minutes. So let's get ready for plugging in the calculator. 0.5 equals e to the 12R. Solve for R. How do you solve for R? Do you remember? That's where we started. So this is technically an algebra problem. How do we solve? We take the natural logarithm of both sides. That will give us 12 will come down, 12R, and we'll divide by 12. Okay. Should I write that out? Natural logarithm 0.5 equals natural logarithm of e 12R ln 1/2 equals 12R ln e goes to 1. R equals ln 0.5 over 12. There's a little formula for you. Okay. You like formulas? Here you go. R equals ln 0.5 p. So I claim if you're looking for half-life and they give you the time, there's a formula for you. We have found it, and hopefully we've found the answer to this particular question as well. So I'm going to use the calculator because it wants it. So I'm going to say, calculator, find me natural logarithm 1/2 divided by, and in my problem it was 12 minutes. So there we go. I have negative 0.05776, blah, blah, blah. It wants the decay rate, okay, as a percentage. So decay just means it's going down, so that implies it's negative. We found the negative number times 100. So I found negative negative 5.77, 5.8%. That's the idea. So in solving this, we found a little formula in case you want to use that. This is only for half-life. If you're finding third life or something like that, then it wouldn't be a half, it would be a third, something like that. Okay. But a lot of times we're interested in half-life. So I thought maybe I'd bring it up. That's a lot because that was our first example. So I had to bring a lot with me. Are there any questions, comments, or concerns about this one? Is there anything you would like me to explain again? Is there anything I can say again about it? I think I have another, I think there's a string of problems like this. I think the next one is similar. Decay rate, yeah. Okay. This one says the decay rate, K, for a particular radioactive element is 2.6, where the time is measured in years. Find the half-life of the element. Okay. We are again finding half-life. We are given 2.6. That's what we found in the previous problem. So we answered with that 2.6 percentage. This time, that's what we're given. Okay. So they're saying K equals 2.6%, and this is decay rate. So that probably means that R equals negative 0.026. just going from the previous problem with our answer going backwards, that would have to be true. They want the half-life. This is in, that means we're solving for time. Solve for time. Y equals the initial amount, e to the RT. They want the half-life. So that means y over y naught equals half. It's just saying we have half of what we started with. Okay. So 0.5 equals e to the negative 0.026 times t. Solve for t. How do you do that? Let's take the natural logarithm of both sides. Brings that down. Natural logarithm of e is just 1. So I find that t equals natural logarithm of 0.5 divided by negative 0.26. That should do it. My friend calculator. Approximation of that is natural logarithm of negative 0.026. 26.7 years. But I know it was years and not minutes. They told me in the original problem it's in years. So I wouldn't have known unless they told me. So that's still half-life. It's naturally decaying. That should get us there. Okay. Going till 18. Let's see what this one brings me. The initial amount of 3,000 grams of lead-210. How much will remain in 110 years? Lead-210 decays at a rate of 3.15% per year. Okay. We have an initial amount. How much will remain after this time? We have a rate. Okay. So that sounds like K equals 3.15%. So R, since it says decay, is negative 0.315. Okay. Our formula. Now this isn't talking about half-life. This is just saying how much is left. It says the initial amount is 3,000 grams. So why not equals 3,000 grams? Okay. And they told me T equals 110 years. So Y equals E 315 to 110 years. My calculator, add that up. 3,000. E years. 3.82 grams. Any questions about that one? Let's see what 16 brings me. The amount of carbon 14 present in animal bones T years after animal's death is given as this function. How old is an ivory tusk if it's lost 17% of its carbon? So how old to me sounds like time. That's reading like time to me. It's saying that it has lost 17% of its original amount. I think we're solving for time in this one. Solve for time. Okay. So it's lost 17%. Well, I don't think I want to set this equal to 17%. It's lost 17%. That sounds like I want to set it equal to 83%. Would you agree with that? It says it's lost 17%. How old is it? So it sounds like it's 83% of what it was. I want to solve for t. How do I do that? Well, I'm going to have that. This is just an algebra problem. It's just a particular sticky one. Let's do it. Natural log of 0.83 equals natural log E. What does that mean? 0.83 negative 2.209 natural log E is 1. So T equals the natural log 0.83 per 0.9 7. Yes, right? Plug in calculator. Seven. Eight. 3 years. Is that one okay? I think when I take screenshots like I'm doing, I think you'll still be able to see the calculator. So hopefully my goal is that if you have to look back at these, that you'll see, okay, he used the calculator for that one. He didn't just know that that's what the answer was. Right. Uranium has a half-life of 4.5 billion years. Geologists find a rock containing a mixture and determine that 61% of the original remains. The other 39 has decayed into lead. How old is the rock? How old sounds like time to me? So it sounds like I'm solved for time to me. That's what it sounds like. They said the half-life is 4.5 billion years. $4.5 billion. So what do we not know? I don't think we know the rate. We know the time, and we know how much is left. We're solving for time, but I don't think we know the rate. I don't think we know the rate. So I think we need to find the rate of the half-life, and then we can figure out time. So we have to, I think we have to kind of build up to it. All right, so the half-life, half is ER, and they said that was 4.5. Now just know that this is going to be in relation to billions of years. So I'm trying to find R first, because I don't know what R is. I know the half-life time, but I don't know what R is. That makes sense? So I'll solve for R. So that's natural logarithm 0.5 over 4.5. And that should give me R. But that's in relation to billion. So we need to natural logarithm 5 divided by tells me the rate. Now I know the rate. Okay. So the original problem said determine 61% of the original is there. How old is it? Now I know the half-life equation. They want 61% is there. 0.61 equals E154 T. Solve for this T. What's that going to be? Logarithm 0.61 less 61% divided by my rate. Equals T. 3.21. And that's not years, that's a billions of years. That's what it said. So I started off with billions of years. Questions on that one? think we have one more of that type that I want to talk about. The amount of carbon-14 present in animal bones after 2 years is given as this function. A bone has lost 25% of its carbon. How old is the bone? It sounds like I'm solving for time. How old? Solve for time. They give me the equation. That was nice of them. E naught E. They gave me the equation. They said it's lost 25%. So how much is still there? It's lost 25%. So how much is still there? Sounds like 75% is still there. Now solve for T. T equals what they give you here. Percent. That would be years. It gave it to me in years. A little over. Questions on that one? Questions on any of that chunk? My half-life chunk. Very, very, very common. Very common to go over this. So that half-life would be something that I would think would have the potential of showing up on the midterm. I don't know which question, but one of them, something like that would be on the midterm. Very cool. I think a few after that are very similar, but maybe a little different, but I'm going to move on to something completely different. I'm going to skip to question 25. Make sure I have time for those. So this is question 25. Hate it. All right. What on earth is going on here? So we have y equals 18 to the x with my numbers. What does that mean? Well, we've had e to the x, right? We had e to the x. What does this mean? I can pull up in the book. There's a demonstration, the derivative of a constant to the variable. So this is different from e to the x. So note that we have right one in green. So they're saying a to the x. What is the derivative of some number? A is a real number. In our case, it's going to be a positive whole number. What is the derivative of this? Well, they show how you define it. What they do is they use the explanation there. So you have a to the x becomes e ln a to the x, which is technically true, right? That's still the same thing. Then they take the derivative using chain rule, okay? So then they find that d over dx of a to the x is just a to the x times the natural logarithm, whatever a is. This is something you're going to want in your notebook, okay? You're going to want that one. You're going to want that on your cheat sheet. Hopefully with practice, you'll just remember. But this is where it comes from. So this is theorem 12. Theorem 12 states it's a derivative of a to the x. A is some whole number, we'll say, as natural logarithm of a times a to the x. We'll need that for the next few problems. So you will want to have that in your notes. Okay. Well, if you accept that from me, then y equals 18x, or whatever version you have, y prime just equals the original function times natural logarithm of 18. Because theorem 12 says d over dx of a to the x equals natural logarithm of a times a to the x. And it's almost 3:30, so I definitely don't have time to do as h approaches 0, a plus h, h, long time for that stuff. We're just gonna have to take it as theorem 12 says this. Okay, so have that written down. Have that written down. Take a look at the book if you're interested where it comes from. So what would this do for us? We have g of t equals 11t. Well then, what is g prime? ln 11 times the original. That's the idea. All right, what about this? So here, well, we could treat it like product rule, but 6 doesn't even have a variable to us. So, I mean, we can say, oh, well, that's f and that's g. So f prime times g plus f times g prime, but it doesn't even, f prime is just 0. We can just directly say, okay, well, then that's y prime equals 6 times the derivative of 3x to the x should be ln of 3 times 3x by theorem 12. Any questions about that? Until 34. What about this one? Now, y equals 3 to the x to the 6 plus 3. Well, I think now it might be time to use chain rule. So let u equal x to the sixth plus 3 du dx 6x to the fifth dy du would be ln of 3 u, so we can build it. dy dx equals dy u times du dx, and that is natural logarithm of 3 to the x times du dx, which was 6x to the fifth. Questions, comments about it? Any questions? I got this one. So it's really just, I mean, we're just tacking on the derivative of the exponent. And then we have to remember logarithm, natural logarithm of the base. Hopefully that's okay. 9. I think this is theorem. Sadly, I didn't write down what theorem number it was, but in the book, I don't want to flip live. 1 over the natural logarithm of a. Write that a little cleaner. Natural logarithm of a times x. That's in the book. See if I can find that. I think it gets its own. Oh, it's probably right here. Here it is. It's theorem. Here's just one more theorem. Theorem 13. It gives a nice proof there that has to be the case. So that's theorem 13 that tells us what the logarithm of base a x is. So we can use that. For examples, so theorem 13 helps us out with that. So here, a equals 11. So y prime just equals 1 over natural log 11 times x. And you can see I have the x to the front. That's okay, that's the same thing. So I would have that in your notes as well. If you're building a cheat sheet, I would have that in your cheat sheet. Theorem 13, that should probably go down. You need that one too. 30. We're kind of building on the last one. So theorem 13 says that the log base a d over dx natural log of a times x. Need that for this one. I think for here, we're going to need to use chain rule. So I'm going to substitute u 5x minus 2. So du dx just equals 5. That's easy enough. Okay. If I have g of u log base 43 of u, what's the derivative of g in terms of u? 1 over natural log 43 times u, 1 over natural log 43 times 5x minus 2. Chain rule, dy dx equals dy du times du dx. That's 1 natural logarithm 43, because that's the base I was given. The original argument, 5x minus 2 times 5. And I'll just, since I can, I'm just going to erase that 1, turn it into a 5, and I'll be good to go. This is either really easy or really hard because I'm losing students by the minute. But I don't know. It's hard to know what you guys are thinking. Hopefully it's going okay. I still got some problems I want to go over. I was hoping to get to at least 34. So I'm going to keep going. We got here log base 7 x to the 4th plus x. All right. Let u equal x to the 4th plus x. That would give me du dx 4x to the 3rd plus 1. So I let y equal log base 7 of u dy du equals 1 over natural log 7 times u. And u be x to the 4th plus x. Multiply it by du dx. ui dx equals dy du du dx dy du is 1 over the natural log of 7 x to the 4th plus x times 4 x cubed plus 1 chain rule. Coming up a lot in this one. Let's see what the next one brings. Okay, finally we got some product here. Great. I'll let f equal 10x and g equal log base 7 of x. Okay, so f prime, well, what does that give me? Natural log of 10 times 10x. G prime gives me 1 over natural log of 7 times x. So I can just build it. All right, so product rule, f prime times g plus f times g prime. So natural log 10 x log base 7x plus 1 over natural log 7x times x. I can clean it up a little bit. And x natural log base 7x 10x natural log 7x. Do 2 more of this type. Let's see what 33 brings us. It looks like it's another product rule to me. We have g, if you'll let me, I'm going to switch that to y. Y equals x to the 4th, 2.8 to the x. So that being the case, I'm going to let this be f and this be g. F prime times g, f times g prime. So if f of x equals x to the 4th, x prime of x equals 4x to the 3rd, g of x equals 2.8x, so g prime of x equals the natural log of 2.8 times 2.8x. Those are my 4 pieces. Now I just build my derivative. So g prime of x equals derivative of f, 4x cubed, times the original g plus the original f times derivative of g Let's see what 34 brings us. Quotient rule. Let's do it. Rewrite this as y equals 3x, 5x plus 3. I'll let f of x equal 3 to the x. So f prime of x equals natural log of 3x. G of x, I'll let equal 5x plus 3. So g prime of x just equals 5. Quotient rule says f prime times g minus f times g prime over g squared. So I just need to build that. Okay. So let's do that. We have natural log of 3x times the original g, 5x plus 3 minus the original f3 to the x times derivative g, and then over g squared, 5x plus 3, just write that as squared. Man. Any questions about that? Big chunk. But other problems. Actually, I mean, I'm good with that, if you're good with that. I have notes coming out for the rest of the problems, and then I have a few word problems that I plan to do a couple of videos on. For all the other problems you do, well, I mean, for all the problems you have step by step, I think that'll be okay. Something like 37. You just gotta kind of walk through it. You know, it's not any worse than what we did. I think what we've done will give you a solid footing of how to begin. You should recognize exponentials now. So at least you should have the foundation to get this. So I think that's enough, and that's quite a lot. I was rushing because I wanted to get through at least those problems. So I'll end the video. Stick around if there's any questions. Don't hesitate to email me if you have any questions, and I will see you next